Hello and welcome to this talk on quantum routing with fast reversals. This is in collaboration with Ani, Andrew, Alexei, Sam, and Rishi, and based on the two papers presented on this slide. In this work, we will consider the following goal, where we want to run a quantum algorithm on a quantum device. However, very quickly we realize that in reality, devices do not match the theoretical requirements we impose on them, or that we assume. And in particular, here we will consider how connectivity constrains gate operations. So for example, if we look at the IBM quantum processor in the figure here below, we see that the qubits here, the black squares, are connected in a planar fashion, and this will constrain how we can perform or where we can perform 2-qubit gates. So what we do is we model this as a graph where vertices represent physical qubits and edges where we can perform 2-qubit gates. So for example, we can perform the unitary U1 between the qubits 3 and 5, but we cannot perform the unitary U2 between qubits 4 and 10 because there's no edge there. And one very useful step to work around these connectivity constraints is routing. So what is routing? Well, if we are given an architecture graph G and the permutation pi that maps vertices to vertices, then we want to implement the mapping that takes the state on the qubits on qubit 1, 2 until n and maps them into the state that is permuted qubit by qubit. So the indices are permuted. And in routing, we can consider many ways to optimize. For example, optimize for circuit depth, for circuit size, evolution time, etc. And in particular, why do we want to study routing? Well, routing bounds the worst case overhead of the architecture. So for every layer of any circuit, we may need to insert the worst case routing overhead because that layer might contain gates that are very non-local. Moreover, routing is actually sufficient to run quantum algorithms on these connectivity constrained devices and allows certain subroutines to make more informed decisions, such as qubit mapping, which is used in this CSU 19 paper. So a natural way to implement routing is to use swap gates. And many papers do this, and this might even be assumed to be the only way to do things. But here we call this classical routing. And now the question is this really all a quantum computer can do? Is classical routing equivalent to quantum routing? So in this talk, we will show that if we allow generic Hamiltonian evolutions, then Hamiltonian quantum routing is actually faster or a stronger routing model than classical routing. And to show this, we will do what we call a state reversal, which we will see is a very fast primitive for routing, and it can be quite useful. So what exactly is state reversal? So state reversal is the mapping here depicted on the left in the figure, where we take qubits on a chain and we map them from one end to the other. So here the qubits 1 and 2 are mapped to n and n minus 1 respectively, and we continue this down the center. So what we propose in our paper is a new time-independent state reversal of a spin chain. And this has the following Hamiltonian. This has a Hamiltonian of the following form, where we have XX interactions on nearest neighbors, and we have local Z and X terms. And we actually show that this implements state reversal 3 times faster than classical routing, which just uses swaps. And while that doesn't sound like a lot, we claim that this matters for the near term because this allows us to execute longer circuits. And moreover, it shows that there is something better that you can do than using swaps. So an alternative way to see this and to implement state reversal in a similar amount of time as our Hamiltonian protocol is the following circuit that we apply n to n plus 1 times, where we do controlled phase gates on every pair of qubits, and then do a Hadamard on every qubit. And this also implements a state reversal. So we show a lower bound on state reversal that that shows that our protocol and also those time-dependent protocols from the previous slide are optimal up to constant factors. So let me sketch a proof in 3 steps. So the first thing that we will need is the entanglement capacity theorem. So this says that the rate at which the von Neumann entropy can be increased by any XX Hamiltonian and local operations and classical communication is bounded above by a term alpha, which is approximately 1.912. And now we construct an instance where this is relevant. So we will construct the following instance where initially we have a system in n bell pairs. So we have a chain and we add 1 ancilla to every qubit, and we initialize every qubit and its ancilla into a bell pair. And if we look at the system, then we see that the entropy across a vertical cut is 0. However, if we perform a reversal on the circled nodes, the red circled nodes, then afterwards we see that the entropy has increased to n. So now if we apply the entanglement capacity theorem, we immediately see that the state reversal time must be lower bounded by n over alpha, because this one operation has increased the entropy by n and the rate is lower bounded by alpha. So we show that our protocol takes a time upper bounded by pi over 4 times n plus 1. And just as a side note, a swap operation takes a time 3 pi over 4. And just to keep things simple, we've normalized by the swap time in the previous slide, which gives us this 3 times improvement. All right, so we know how to do state reversal, and in particular, we know how to do it much faster than we can do swaps. But we are kind of interested in how we can do general routing, so implement general permutations. And in this section, we will see how to build fast routing from fast reversals. So routing that's faster than swaps using these reversals. And an illustrative first step is sparse permutations, which may also be of independent interest. So let's say we have a K-Sparse permutation, and that means something as follows. So let's say we have a 6-sparse permutation. That basically means that we have 6 qubits that need to be routed. So here we have 6 qubits that need to be routed, one that needs to be routed to the 5th one, the second one needs to be routed to the 3rd one, etc. And the rest of the qubits need to stay in place. So what we can do here is we can use reversals, since this is a spin chain, to route the qubits to the center as follows. So first we reverse the qubits at the outer ends, and then reverse the next set of qubits, and then finally the last 3. And now that all the qubits are located in the center, we have a chain of length k that needs to be routed, and there exist routing algorithms to do that within k time. And then we simply reverse the first couple of steps to finish our routing protocol as follows. And then we're done. So this is a very simple routing algorithm for K-Sparse permutations on chains. And in particular, we have the following statement. We have that on a path graph of length n, we can route any permutation pi in a time at most n over 3 plus k squared. So to compare that to swaps, we see that swaps take at least n minus 1 time. So we have obtained an advantage for small k. Now, using slightly more sophisticated techniques, we can actually generalize this to any graph G with a radius r, where we can route pi in a time at most 2r over 3 plus k squared. So this, again, obtains the path result, however, allows us to apply it to any connected graph. Okay, so we know now how to do reversals. We know now how to do sparse permutations. How do we do general permutations, in particular worst case, where every qubit needs to be routed? And we will construct that from sorting. So what we do is we can use a binary sorting algorithm that uses fast reversals to make a routing algorithm. And what is a binary sorting algorithm? A sorting algorithm, that is a sorting algorithm that orders a bit string of zeros and ones in ascending order. So what the first step that we need to do is we apply a labeling function which assigns 0 bits to the qubits that need to be routed to the left half of the chain, and 1 bits that need to the qubits that need to be routed to the right half of the chain. So when we apply this to a permutation, here the permutation is 760255134. So the first qubit needs to be routed to the 7th position, for example. And we apply our labeling function, then we get the bit string that I wrote down below the permutation here. And if we apply our sorting function, then the bit string will be sorted in ascending order. And if we then use the same reversals that were used in the sorting function, then we get the permutation that's shown above. So very straightforwardly, we can now apply a divide and conquer strategy, since this very nicely splits our chain to 2 parts that need to be routed separately. So if we look at the left and right side separately and apply the same strategy recursively, we get the following result. And now if we apply this once more, we get our routed permutation. So how do we implement this sorting? And in particular, how do we do it fast? Or quickly? So what we do is we define an algorithm we call tripartite binary sort, or TBS, and we do that recursively. So once we're given, if say we're given a bit string, which I won't pronounce here, and split it into 3 parts, so it's tripartite, and then we apply TBS on the left, middle, and right half independently, where in the middle we actually sort backwards. Then if you look at this closely, you can see that we can sort the result in using just one reversal. So this is the merge step of this recursive algorithm. And now we show that we can actually implement this quickly because there is a constant epsilon, approximately 0.017, such that adaptive TBS, which is a slightly modified TBS, sorts any bit string B in time 1/2 minus epsilon times n, plus subleading logarithmic terms. So this actually shows that we can do slightly better than n over 2 time to sort, and this will allow us to show that we have a fast routing algorithm. So if we take this theorem and we directly apply it to the divide and conquer strategy that I showed a few slides ago, then we get the following corollary. We show that we can route any permutation pi in a time at most 1 minus 2 epsilon times n, where epsilon is this positive constant. So therefore, since we know that any swap-based protocol takes a time at least n minus 1, this gives us our first quantum classical separation for routing. We also implemented this algorithm in software and sampled many permutations randomly and plotted here the normalized routing performance of our algorithm, TBS, versus that of swaps. So that is odd even sort, or OES. And we see on the top here that OES, so swaps, approaches 1 for large n, and whereas our algorithm approaches 2/3 for large n. And another thing you may notice is that for n 50 or larger, the differences are already quite significant. So actually, from these results, we were motivated to prove that it was the case that these algorithms approach these quantities. And we actually showed in an average case analysis that OES must approach an average case of 1, whereas our TBS algorithm must or will approach a time of 2/3 n. So to conclude, we saw that state reversal is possible in a time 3 times faster than any swap protocol, and that this is tied up to constants. We also showed the first quantum classical routing separation using fast reversals and a sorting algorithm. And finally, we also showed fast routing for sparse permutations. So in future work, we may want to tighten this upper bound of 1 minus 2 epsilon n plus some leading terms, since the empirical results and our average case result indicate that the performance approaches is 2n over 3. And so a pretty significant improvement might still be possible. However, we cannot hope to get anything more than a constant factor improvement by our lower bound result. So we are forced to look at other graphs to find super constant routing separations. And this is currently a work, currently something that we are looking at. So another angle of approach to this problem is to find lower bounds on quantum routing. And in particular, we know that Lieb-Robinson bounds bound the non-relativistic speed of quantum information as kind of like a physics angle to this problem. And we are working on lower bounding the speed at which we can implement routing on these graphs. And of course, we can also go beyond the two models that we've seen in this talk. So say we introduce in between classical routing and Hamiltonian routing, we can also find what we call gate-based quantum routing, where we limit our model to gates that are applied, and we try to minimize the routing depth, so the circuit depth to implement routing. And this lies somewhere in between classical routing and Hamiltonian quantum routing. So thank you for your attention, and have a good day.